Hello students, we'll be learning about the comparison of bond angles in different molecules. This is based on the study of hybridization and VSEPR theory, which you must have done earlier. We'll be using the concepts learned in hybridization and VSEPR theory to compare the bond angles in different molecules. Let us study the factors to compare the bond angles one by one. The first factor that will used to compare the bond angle will be the hybridization of the central atom. First factor for comparison of bond angles in different molecule is hybridization of the central atom. Let us discuss this with the help of an example. We already know that for different hybridization of the central atom, the bond angles are different. Okay? A simple case can be an sp hybridized central atom will result in a bond angle of 180 degree. The bond angle is greater than the sp2 hybridized atom, where bond angle is 120 degree, will be greater than the sp3 hybridized atom, where the bond angle will be 109 degree 28 minutes. So as the hybridization of the central atom will change, the bond angles will change. Okay. Let us do some simple examples based on this. Let us compare the bond angles in SO2 and CO2. They appear to have similar formula. One sulfur atom, two oxygen atom, one carbon atom, two oxygen atom. They have similar formula, but they have different hybridizations for the central atom. SO2, sulfur as a lone pair and two sulfur oxygen double bonds. CO2, there is no lone pair on carbon. There are two carbon oxygen double bonds. So two double bond oxygen atoms are present in both CO2 and SO2, but there is no lone pair in CO2, but there is one lone pair in SO2 molecule on the central atom. As a result, the hybridization of SO2 is sp2 and that of CO2 is sp. But definitely bond angle in CO2 will be greater than bond angle in SO2. When hybridization is sp2, bond angle is close to 120. For a perfect 120 degree bond angle, all the bonds have to be identical. We have discussed this in VSEPR theory. Presence of lone pair decreases the bond angle. The actual bond angle in SO2 is slightly less than 120, but it is close to 120. Whereas for an sp hybridized atom, for a linear structure, the bond angle will be 180 degree. Theta will be 180 degree. Definitely CO2 has a bond angle that is greater than the bond angle in SO2. Let us do some more examples. Let us compare the bond angles in, suppose, BF3 and SiF4. BF3 and SiF4. Comparing the bond angles in BF3 and SiF4. BF3 boron bonded to 3-fluorine, no lone pair on boron. Boron is sp2 hybridized. SiF4 silicon bonded to 4 fluorine atoms. Silicon bonded to 4 fluorine atoms, no lone pair on silicon. It will be sp3 hybridized, it will have a tetrahedral structure. Okay. Accordingly, we can write the bond angles. On an sp2 hybridized atom, bond angle is 120 degree, whereas on an sp3 hybridized atom, bond angles will be 109 degree 28 minutes. So it's clear that the bond angles in BF3 molecule are greater than the bond angles in SiF4 molecule. The first point is to compare the hybridization of the central atom. If the hybridization of the central atom is different, then definitely we can find out we can compare the bond angles based on the hybridization of the central atom. We have already studied the bond angles for different hybridization in the previous lectures. Next point. If hybridization of the central atom is same, then how to compare the bond angles? So second point, we'll use the second point only when hybridization is same. If hybridization is same, then we check for the number of lone pairs on the central atom. We check for number of lone pairs on the central atom. We have discussed in VSEPR theory that as the number of lone pairs on the central atom increases, the lone pair repulsion is stronger than the lone pair bond pair repulsion is stronger than the bond pair repulsion, which increases the repulsion by the lone pair and which decreases the bond angles between the molecules. We can write that the bond angle is inversely proportional to number of lone pairs. There is no such mathematical proportionality, but we can simply say that as the number of lone pairs on the central atom increase, as the number of lone pairs on the central atom increase, the bond angles will decrease. Bond angles decrease. Let us consider an example based on this, comparing the bond angles in CH4, NH3 and H2O. Let me draw the structures of CH4, NH3 and H2 on the next page, comparing the bond angles in methane, ammonia and water molecule. These are very commonly occurring molecules. In case structures, their structures and their hybridizations we have already studied. CH4 has a tetrahedral structure, is sp3 hybridized. NH3 is also sp3 hybridized, has a tetrahedral geometry, but shape we call it as trigonal pyramidal. H2O has a bend shape. Although its hybridization is same as sp3, but it has two lone pairs on oxygen atom, it has a bend shape. The lone pair repulsion is more than the lone pair bond pair repulsion, which decreases the bond angles significantly. The bond angles are represented as theta. All are sp3 hybridized, all have same hybridization for the central atom. But the bond angle theta is perfect, 109 degree 28 minutes in CH4 molecule. Bond angle is slightly less than 109 degree in an ammonia molecule. It is around 107 degrees. And that in water molecule, it is even lower than in ammonia because presence of two lone pairs will further decrease the bond angles. The value of theta is around 104.5 degrees in water molecule. Thus, from this example, we can illustrate that more is the number of lone pairs on the central atom, the bond angles will decrease. Another similar example we can take comparing the bond angles in NH4 plus, ammonia and NH2 minus. This is also a similar example. NH4 plus, nitrogen bonded to 4 hydrogen atoms. There is a formal positive charge on the nitrogen atom. Ammonia, nitrogen bonded to 3 hydrogen atoms and having a lone pair as above. And NH2 minus, nitrogen will have 2 lone pairs in NH2 minus with a negative charge. Nitrogen with a negative charge, nitrogen having 2 lone pairs. Presence of lone pairs will decrease the bond angles. Okay? So we can say that if this is theta 1, this is theta 2, and this is theta 3, more is the number of lone pairs on the central atom, the bond angles will decrease. Theta 1 greater than theta 2, greater than theta 3. Is it clear? So we see that in all these examples, in both these examples, as the number of lone pairs on the central atom increases, the bond angles decrease. Okay. Next point. We have discussed 2 points till now. First point was hybridization of the central atom, and the second point is the number of lone pairs on the central atom. Okay. Now the third point, if the hybridization is same and there is no lone pair. If hybridization is same and number of lone pairs is 0. In that case, bond angles are equal. In that case, bond angles are equal. Let us take examples of this, which will help us in better understanding of this point. Hybridization is same and number of lone pairs is 0. Let us consider the example of BF3, BCl3, BBr3 and BI3. All are sp2 hybridized and have no lone pairs. None of them have any lone pair on the central atom. It satisfies this case. What is this case? Hybridization is same and there should not be any lone pair on the central atom. There should not be any lone pair on the central atom. All these are perfect sp2 hybridized. They have perfect trigonal planar geometries. The bond angles are perfect 120 degree in all these molecules. BF3, BCl3, BBr3. The bond angles are perfect 120 degree. All these molecules have identical bond angles. We can say that bond angles in these molecules are equal. BCl3 is equal to BBr3 is equal to BI3. Is it clear? If hybridization is same and there is no lone pair on the central atom, then the molecules will have identical bond angles. An example can be BF3, BCl3, BR3, BI3. Another similar example we can think of CH4. Bond angles are perfect 109 degree 28 minutes. CF4 carbon tetrafluoride, CCl4 carbon tetrachloride, SiCl4 silicon tetrachloride, etc. All these molecules are sp3 hybridized. All these molecules, none of these molecules have lone pairs on the central atom, no lone pair on central atom. Therefore, all these molecules will have identical bond angles. That is the bond angle of tetrahedral bond angle of 109 degree 28 minutes. Fine. Is it understood? So let's move on to the next point. Okay, I'll do this the next point in the next page. The next point is just wait.